Okay, so this is joint work with Anand Oza and Dimitar Ostrev, who are both graduate students at MIT. And I'm going to start with a little background of quantum mechanics. To a physicist, one of the fundamental principles of quantum mechanics is a superposition principle, which says if you have two mutually distinguishable states, A and B, it can be in both of these states at once. So it can be in the superposition of states alpha A plus beta B, where alpha and beta are both complex numbers, and alpha squared plus beta squared is 1. And if you look at this system, the chance of seeing it, so if we look at the system we assume that the two states were mutually distinguishable. If we look at it using the algorithm we use to distinguish these two states, or the measurement there, it will say we're in state A with probability alpha squared and state B with probability beta squared. To a mathematician, what the superposition principle says is that the state of a quantum system is a unit vector in a complex Hilbert space. Thank you. C to the D for finite dimensional systems. And measuring the system projects the vector onto one of a set of orthonormal basis vectors with probability proportional to the square of the length of this projection. So what I want to talk to you today is, a question which arose in quantum information theory. And it turns out the same question, or actually a very similar question, arose in the study of operator algebras. And Anand Oza and I solved the question last spring, and simultaneously Musat and Hagarup solved it in the operator algebra version. And we met at a conference in June. And I think actually this, there are a lot of interesting things from von Neumann algebras which at least somewhat impact quantum information theory. And I'll get to that later in this talk. But first I want to talk about the question we were asked, where we were thinking about, and how we solved it. So we'll call a two-dimensional quantum system a qubit. And if you have polarized photon, there are only two distinguishable states, vertical and horizontal. And all other states are linear combinations of these states. So right circular polarization is 1 over √2 vertical plus I, or horizontal plus I vertical, and so forth. But whenever you have a measurement which distinguishes two possibilities, they have to be orthogonal vectors in this Hilbert space. And if you have two qubits, their joint state space is a tensor product of their individual state spaces. And now you can have two qubits which can be in a state which is an EPR pair, so 1 over √2 vertical horizontal minus horizontal vertical. And you can change the spaces. That becomes right diagonal, left diagonal minus left diagonal, right diagonal. And neither quantum bit alone has a definite state. So these states are called entangled states. And mathematically, it's just something in the tensor product state space which is not a tensor product. So if you have n qubits, their joint state is described by a 2 to the n dimensional vector. So the basis states of this vector space are all bit strings of length 2n, whereby this we mean the tensor product of 0 in the first system and 1 in the second system, etc. And the high dimensional tensor product space is where quantum information theory lives. So in quantum information theory, we will be working with density matrices rather than quantum states. So what a density matrix is a d by d Hermitian trace 1 positive semi-definite matrix. And there's a correspondence. Wait, where's this? Yeah. And there's a correspondence between density matrices and pure states. Density matrices can arise from pure states in two different ways. One, you can get probabilistic ensembles of pure states, or two, you can get states of subsystems of pure quantum states. So if you have a probabilistic quantum state, which is a state VI with probability P sub I, the corresponding density matrix is the convex combination of the pure states VI dagger, where the VIs are the the states in this probabilistic ensemble, and VI dagger gives rank 1 matrix, and then you take the convex combination to get a density matrix. And one important thing about density matrices is they give as much information as is possible about outcomes of experiments performed on the system. So two systems with the same density matrix rho are indistinguishable. If you have a joint quantum system on Hilbert space of size A, tensor Hilbert space of size B, and you throw away this second part of the system, the first part of the system is effectively in the state the partial trace on B, rho sub AB. And this means, again, that any experiment you perform on the system, the probabilistic outcomes can be predicted from rho sub A if you do not have access to the second part of the system. And here, this is the partial trace over the second quantum space. And if you have a tensor product state, rho AB, which is rho A, tensor rho B, then the partial trace is just take the trace on the second part and multiply it by the first part. And if you extend this linearly to define the partial trace on entangled states, that's the definition of the partial trace. Okay. And if you're given a set of positive semi-definite matrices, E sub I, the probability of the so the most general measurement on a quantum system is given by a POVM. So if you're given a set of positive semi-definite matrices, E sub I satisfying summation I, E sub I is the identity matrix, then the probability of the ith outcome is trace of EI times rho. So most people probably know about the von Neumann quantum measurements, which is the projection onto states of a basis. So this is a generalization of that. If you have a von Neumann measurement, you have a basis E sub I, then the probability, and you let this POVM element be E sub I dagger, the probability of the ith outcome is trace rho sub I EI dagger, which is E sub I dagger rho E sub I, which is, probably looks a lot more like the formula you learned for outcomes of measurements in quantum mechanics. Okay. So this talk is going to be about the classification of quantum channels. And if you have a memoryless quantum channel, phi is a completely positive trace-preserving linear map. So a quantum channel is really the most general thing, a way a state can undergo evolution. So this is the most general linear map from density matrices to density matrices. So it has to be it has to be linear because quantum mechanics is linear. It has to be trace preserving because it has to take quantum states to quantum states. Quantum states are trace 1 matrices, so it has to take trace 1 to trace 1. And it has to be positive because you want it to take positive semi-definite matrices to positive semi-definite matrices. And it has to be completely positive, which means even if phi is tensored with the identity map, phi tensor I stays positive. So, this is a fairly abstract characterization of quantum channels. There's much more concrete ones. Any quantum channel can be represented as summation over I, A sub I, rho, A sub I dagger, where the A's satisfy the second condition. Summation A sub I dagger, A sub I is I, and the second condition is required for phi to be trace preserving. And there's a third characterization, which says, and this characterization actually is going to be pertinent to the rest of the talk, or more pertinent. So any quantum channel can be implemented by first embedding the input space into a larger Hilbert space. So you do this by taking your input state rho and tensoring it with a second Hilbert space, which starts out in some fixed state sigma. You then apply a unitary map on this. The unitary map maps rho tensor sigma to U rho tensor sigma U dagger. And then you take the trace on the second system, which is a system you adjoined, and that takes you back to phi of rho. So you can see that this, if you believe that you can implement any unitary transformation, this gives you a way of implementing any positive or completely positive map by adjoining a second system and then discarding the second system. Okay. So now I need to go back and recall Birkhoff's theorem, which is the theorem that, the theorem from probability theory. Every doubly stochastic matrix is a convex combination of permutation matrices. So here's an example, if I got the arithmetic right. And what this says in terms of probability theory is that any doubly stochastic map, so any stochastic map which takes the uniform random distribution to the uniform random distribution, that's what it means by to be doubly stochastic. So I see I left out the uniform random distribution to itself here, can be represented as first doing some probabilistic coin flip and then mapping it by a deterministic permutation map. So people wondered, this is a very old result now, people wondered whether the same thing was true for quantum maps that take, I have left out the definition of a unital map. A unital map is one that takes the identity matrix to itself. So phi unital, if and only if phi of I equals I. So, the equivalent of the completely random distribution, 1 over n for all states, is the identity divided by d, the dimension of the space. And so if you require that a quantum map takes the completely random distribution to itself, the condition is phi of I over d equals I over d, or phi of I equals I. So you can ask whether every unital map can be represented as a convex combination of unitary maps.
Why exactly unitary?
What?
Why unitary?
Well, unitary are the ones, so the unitary are the ones that that do not increase the entropy of the system. So if you apply a unitary map to a quantum system, the entropy remains the same. If you acquire any other quantum map to the system, it increases the entropy.
This is non-commutative analog of permutations.
This is what?
Non-commutative analog of permutations.
Mm-hmm.
It's just one-to-one vector.
Right. So unitary is the equivalent of permutation. And this isn't true, and it's not hard to see that this map, where rho goes to summation I, AI row, AI dagger, satisfies the conditions for it to be unital, so it maps identity to itself. It's it's a quantum map because summation AI dagger is I, and it's not a convex combination of unitaries.
Maybe a combination of isometric matrices.
Isometric are unitaries. Yeah. So, what Andreas Winter and some collaborators wondered was, is this true asymptotically somehow? So suppose you have a quantum map phi. You can look at the tensor product. Okay, so I have another typo there. There should be phi to the tensor product n. So you can look at the tensor product of n copies of phi and ask whether this can be arbitrarily well approximated by unitaries as n goes to infinity. And they conjectured that it could be. And what we're going to show is that this same map in 3 dimensions is not approximable by unitaries as n goes to infinity. And, well, you have to get the definition of well approximable. And since this process involves a limit of phi to the n, phi to the tensor power n as n goes to infinity, it's operating on larger and larger Hilbert spaces, which means you need to specify the norm. If you're in finite dimensions or fixed finite dimension, the norm doesn't matter because they're all equivalent. But here, the correct norm to use is a diamond norm, and I'm not even going to define it because I'm not going to go into the details of this norm. I'm going to wave my hands whenever we need to use this diamond norm.
Above degree is also tensor in the second string, the second string. Above.
Yeah, this should be a tensor too.
Also tensor.
Yes. They both should be tensored. I made a typo. Okay. So let's recall that any quantum map can be written as phi of rho equals trace to u rho tensor sigma u dagger. What we're going to define is an exactly factorizable map, is one that can be written as phi of rho is, well, we require that the sigma be the maximally mixed state, or the state which is essentially as random as possible, so in over n. So we'll define an exactly factorizable map as one that can be written as phi of rho equals trace to u rho tensor I sub n over n, u dagger for some n. And this definition, exactly factorizable, comes to correspond with the operator analysis theory, which uses the definition factorizable, and we'll get to that later. But for now, this may not be the is not the most obvious terminology, but this is what I'll use. And now, I want to claim if phi to the tensor power n is a convex combination of unitaries with rational coefficients, then phi is exactly factorizable. Okay, and the proof is fairly straightforward. Suppose that phi to the tensor power n of rho is equal to a convex combination of unitaries. So 1 over m, summation j equals 1 to m, uj rho, uj dagger. And here we can have equal weights on the unitaries because we're assuming rational coefficients, which means we can just use one unitary many times if there's alpha over m, and put everything with a common denominator. And now let's define a unitary map V as follows. We'll map V of W, which is an auxiliary quantum system, tensor J, or rather, U, W, tensor J. J is the auxiliary constant quantum system, to U sub J, this UJ up here, WJ. And now, if you look at this V, if you take rho 1, tensor I over d to the n minus 1, tensor I over m, and see what happens to it when you apply it with this V. The first thing that happens is you take this So this W is tensor power of n different quantum systems. So this is the first system. This is the next n minus 1 systems. And this is the system we've adjoined, which has dimension m. So we're going to take rho 1 tensor I over the dimension of this thing. So this is the definition of an exactly factorizable map. I mean, this is an exactly factorizable map by its definition. And that turns into, and we're going to, this trace of 1 bar means take the trace, partial trace on everything except the first system. That turns into same trace. Well, we'll take the trace on the last system first. That gives us 1 over m summation j equals 1 to m uj times this u sub j dagger. And now, because this, this was phi, this was phi to the m. This is, you get phi of the first system, and then you get the identity for the rest of the system. So that's trace 1 phi to the m times d to the n minus 1. Okay, I left out a factor of d to the n minus 1 here, times this, which is just phi of rho. So if you have if you have a convex combination of unitaries with rational coefficients, then phi is exactly factorizable. And now we'll define strongly factorizable maps to be the closure of the set of exactly factorizable maps. Right, yeah, so strongly factorizable maps are the closure of the set of exactly factorizable maps. So anything that's a limit of exactly factorizable maps we'll call strongly factorizable. And the theorem is if phi satisfies the asymptotic Birkhoff conjecture, then phi is strongly factorizable. And the way we prove it is we use this, this is the basic idea. If something is the limit of, let's see, if phi satisfies the asymptotic Birkhoff conjecture, then it's the limit of, then as you get larger and larger tensor powers, they get closer and closer to being well approximated by a convex combination of unitaries. And you basically use the same idea of this proof and take limits. And I'm not going to go into the details of that. So what we showed was that the same map we defined well in before. Okay, well, no. The same map here is not strongly factorizable. So here, what this map does is it either projects it into the first two systems, or the first and third system, or the second and third system, and then it swaps the two basis states of these two-dimensional projections. So you can see that if you apply it to the, matrix 1, 0, 0, it either projects it onto the first two or the first and third, and then when it swaps it, you end up with this density matrix. Or if you didn't follow that, it's just a completely straightforward calculation. So if you put 1, 0, 0 into this map phi, it should come out 0, 1/2 diagonal matrix. And now, suppose we have some u, if phi of rho is equal to trace u rho u dagger, and we let u be a, b, c, d, e, f, g, h, i, then u of rho 1 tensor identity is equal to a dagger, a d dagger, a g dagger, etc. And now, if you want to take the trace of this, you just take the trace of all, the partial trace of this, you just take the trace of all these matrices. And now by matching results from phi of rho, we see that phi of trace of a dagger equals 0, so we have to have a equals 0. And we also have to have that 1 over n trace of d dagger equals 1 over n trace of d dagger equals 1 over n trace of g dagger equals 1/2. So, of course, the fact we chose 1, 0, 0 is, we could have done the same thing for 0, 1, 0 or 0, 0, 1 because it was symmetric. So this shows that the diagonal is 0 and the trace of d dagger equals trace of g dagger equals trace of h dagger, etc. is n over 2. And, you know, this also says the trace of a d dagger equals 0, etc. But we won't worry about that now. Okay, so now we've shown that u has to look like this. So u dagger equals u dagger u equals I. And this gives us more constraints. b dagger plus c dagger is I. d dagger plus ff dagger is I, etc. And cf dagger equals bh dagger equals dg dagger equals 0. And, you know, you also have u dagger u, and this gives us all these constraints. And now we have gg dagger plus hh dagger is I from the previous slide, and gh dagger equals 0 from the previous slide as well. We can multiply this on both sides by h, so we get h dagger h equals h, which is a very nice equation. It shows that the eigenvalues of h dagger h are either 0 or 1. Okay. So recall that trace of h dagger h equals n over 2. Okay, that's because if you have an eigenvalue of 1, if you have an okay. I don't know if you can see that directly from this equation, but multiply on the left by v, and you get hv equals vh equals vh h dagger h, and either vh equals 0, in which case the eigenvalue is 0, or vh equals vh here, in which case the corresponding eigenvalue has to be 1. So recall that trace of h dagger h equals n over 2, so we have to have exactly n over 2 eigenvalues of 0 and exactly n over 2 eigenvalues of 1. And by this, we get that the column space of G is perpendicular to the column space of H. So here we have more detail than the last slide. G dagger has n over 2 values of 0 and n over 2 eigenvalues of 1. The singular value theorem says that you can write G as summation k equals 1 to n over 2 vk wk, where vk and wk are the right and left eigenvalues of G, with eigenvector of G with eigenvalue of 1, and that means vk's are orthonormal, and the same is true of H. And now we see that the column space of G is orthogonal to the column space of H, since G dagger is summation vk. And now the rest of the thing is, by looking at inputs other than row 1 into the map phi, we can see that trace of G dagger has to be n over 2. And this can only happen if the column and row spaces of C and G are equal. Let's see. I think I'll skip the proof of that. But here, remember, it looked like B, C, D, F, G, H. So this says that the column space of C is equal to the column space of F, is perpendicular to the column space of D, is equal to the column space of G, is perpendicular to the column space of H, is equal to the column, B, wait, where are we? Yeah, so if you if you go down, the column spaces have to be perpendicular, and if you go diagonal, the column spaces have to be equal. So we go down, diagonal, up, diagonal, up, diagonal, we get back to B, and we've taken the perpendicular, which means the complement 3 times, and we, you know, there are 2 subspaces at n over 2, so we're supposed to get back to itself, but we can't. So this is a contradiction. Okay. So how about strongly factorizable? Well, we need to show that we cannot approximate this unital map with an exactly factorizable map, or rather with a, I'm sorry. So strongly factorizable was the closure of exactly factorizable. So we have to show that we cannot approximate this unital map with a sequence of exactly factorizable maps which have a limit of the sequence. And the proof goes along the same lines, but we need to worry about lots of approximations. And I mean, they're nice, but they're also technical details. You've seen the real meat of the proof, so I won't go into any more details. So now I'm going to say what happened after I discovered, you know, after we did this research. I went to a conference in, I think, June, and discovered Hagerat and Muzak had done similar work. But their definition is a factorizable map. It's one which can be represented as phi of rho equals, okay, I'm going to represent this as, you know, this is not the notation the operator algebraists use, but this is essentially the same thing. So instead of U being an n by n matrix, it's an automorphism of some operator algebra, where you have, well, you take a von Neumann algebra, which is a general, you know, infinite dimensional generalization of some quantum system, and then you take the set of d by d matrices over this von Neumann algebra, which is another von Neumann algebra. So d by d matrices with elements of this von Neumann algebra in them. And tau is a tracial state of the von Neumann algebra, which is essentially a trace. I mean, it's very similar to the identity state for a finite dimensional matrix algebra. So you take trace 2 of U, rho tensor tau, U dagger. And so the only difference here is that we're using von Neumann algebras instead of n by n matrices.
Infinite dimensional?
What? Infinite dimensional, yes.
Sorry, finite?
Infinite dimensional von Neumann algebras.
Could be infinite dimensional.
Yeah. Okay. And for von Neumann algebras, you don't need to worry about limits. If you have a limit of these things in von Neumann algebra, there's another von Neumann algebra which gives you the behavior in the limit. So that's a theorem. I'm not claiming I understand any of the stuff relating to von Neumann algebras, but it's there. And Hagerup and Muzak showed that this map, which is almost exactly the same map, except you have a minus sign, and their techniques work for our map and our techniques work for their map, is not factorizable. And they have a number of other results showing that other maps are not factorizable. And now comes what I think is the interesting part. We have a whole bunch of different types of unital maps. Remember, a unital map is a map that takes the identity to the identity. And then there's factorizable. That's a subclass of unital maps. There's strongly factorizable, which is a subclass of factorizable, because strongly factorizable is just the case where the von Neumann algebra is the n by n matrices. And strongly factorizable is the limit. Exactly factorizable is the case where the von Neumann algebra is the n by n matrices for some n. And strongly factorizable is the limit of exactly factorizable maps. And then we have this thing. I'm going to call this the asymptotic quantum Birkoff property, which are maps which satisfy the asymptotic quantum Birkoff conjecture. In other words, they can be arbitrarily well approximated. The tensor product of n of these maps can be arbitrarily well approximated by mixture of unitaries. And then we have convex combinations of unitaries at the bottom. So what do we know about these? Well, so Hagerup and Musat showed that unital maps were not factorizable. We showed unital maps and strongly factorizable maps were not the same. And we also, there's a paper that shows that mixtures of unitary, that there can be maps that satisfy the asymptotic quantum Birkhoff conjecture, which are not mixtures of unitaries. And now, interesting thing is that factorizable is equal to strongly factorizable if and only if something called the Kahn's embedding conjecture is true. And I can get to the Kahn's embedding conjecture later, but no. And then I know nothing about this and this, whether they're equal or not. So what is the, well, first question is convex combination of unitaries. So Mendel and Wolf in 2009 computationally investigated the set of unital channels, and they found cases where phi, tensor phi, was a convex combination of unitaries, but where phi by itself was not. And this was, I don't want to say it's numerical work, but it's computational work. They looked at a special subclass of unital channels and figured out when phi tensor phi was a convex combination of unitaries and when phi was a convex combination of unitaries, and miraculously they were different.
Very big matrices probably.
I don't think they were very big. I mean, I have the paper here. We can look at it later. I think, they were, I mean, the class of matrices were actually a class of n by n matrices with lots of symmetries. So but I think they were different in relatively small dimensions. So now I want to say something about this proof. These are equal if and only if Kahn's embedding conjecture is true. So to do this, we need to look at a subclass of unitaries, which are called Shor contractions. So a Shor contraction is one where rho sub ij goes to alpha sub I, rho sub ij, independent of the input matrix. So I should have given an example, but I can give one. If alpha sub ij is equal to, let's say, 1, 1, 1 half, 1 half, this will take the matrix 2/3, 1/3, 1/3, 1/3, 2. Well, what you do is you multiply this, you multiply matrices pointwise. So 2/3, 1/6, 1/6, 1/3. And first thing about Shor contractions is that they're completely positive if and only if alpha sub ij, that's this map you multiply things by, is Hermitian and positive semi-definite. Oh, yeah, yeah. Okay, so recall from Choi's theorem that a trace-preserving linear map phi is a quantum map if and only if you take phi tensor I. So you apply phi to the first part of a system and I to the second part, and you apply it to a maximally entangled state, which you can represent this way: 1/d, summation I equals 1 to d, I, summation I equals 1 to d, I. So take this state, and then, this is a one-dimensional, a rank 1 projection matrix onto this state. And if you apply phi tensor I to this state, and the result is positive semi-definite, then this quantum operation is, then this is a completely positive map. So it's a quantum operation. So for a Shor contraction to be a quantum operation, we require that this is positive semi-definite, which is the same as saying that the matrix alpha sub ij is positive semi-definite. Now, suppose you have a Shor contraction that's factorizable. Then, well, the Shor contraction has to map, any Shor contraction has to have ones along the diagonal. And so it has to map 0, 1, 0, 0 to 0, 0, 0, 1, 0, 0, 0, 0. And that means if you have a unitary map for which trace on the second part of u rho tensor I u dagger is 0, is this way of getting for the definition of factorizable, u I phi had better be I times some unitary operation on phi. So ui phi is equal to I u sub I phi. And now you take the trace of u I j tensor I, u dagger. I seem to have left out normalization here. You should get ij times trace of ui uj dagger.
Maybe in the last formula you were someone is called d.
Yeah, there should be a d.
Yeah.
1 over D.
1 over d. 1 over d, yeah. So we have to have alpha sub ij is equal to 1 over d trace of ui uj dagger. So yeah, I've left out all sorts of constants in this. Alpha ij equals 1 over d ui uj dagger trace. So you can ask, which matrices are, I'm used to working with a normalized trace where I'm sorry, in the operator algebras you work with a normalized trace where they stick the 1 over d in the trace. And I should have, so let E sub d be the exactly factorizable contractions in dimension d, where alpha ij equals 1 over and trace ui uj dagger. And now let gd be the set of factorizable Shor contractions in dimension d, where you have a von Neumann algebra. So there's a theorem by Dekena and Jushenko that the closure of E sub d equals g of d. So the closure of exactly factorizable Shor contractions is factorizable Shor contractions if and only if Kahn's embedding conjecture is true. So we are dealing with strongly factorizable Shor contractions. And we can use this theorem to show that Kahn's embedding conjecture is true if and only if the set of strongly factorizable maps is equal to the set of factorizable maps. So this direction, well, we know that the limit of strongly factorizable Shor contraction, we know that the limit of exactly factorizable Shor contractions is equal to a Shor contraction is, okay. Okay, so.
Will you say what is quantum embedding conjecture?
Yes, I will. So, so here we have exactly here sub g sub d is a, Kahn's embedding conjecture is equivalent to g sub d to all factorizable Shor contractions being a limit of exactly factorizable Shor contractions. And here, what we want is that all factorizable Shor contractions, to prove it to prove that if strongly factorizable maps are factorizable maps, we need to show that the limit of every limit of exactly factorizable maps that happens to be a Shor contraction we know that every factorizable Shor contraction has to be the limit of factorizable maps, which happen to be a Shor contraction. So here we only need to show that every strongly factorizable Shor contraction is a limit of exactly factorizable Shor contractions. And we can do this by basically taking this limit of these exactly factorizable maps that gives a Shor contraction and showing how to turn each of these into a Shor contraction which approaches the limit. And the other way is actually fairly standard using Kahn's embedding conjecture and theorems about von Neumann algebras, which I will tell you about now. So what is Kahn's embedding conjecture? So Kahn's embedding conjecture is so a von Neumann algebra is a type of C-star algebra which is, closed under limits, closed under weak limits, and closed under duality. So, von Neumann algebras can be classified into type 1, type 2, 1, type 2 infinity, and type 3. And type 2, 1, these have a trace so these have a trace, and there's also so if you have a trace, you want to, and trace of the identity is equal to 1. So if you, and these are essentially finite dimensional matrices, or infinite dimensional matrices. So if you have a type 2, 1 von Neumann algebra, that's the same, that's equivalent to taking type 1 or taking finite dimensional matrices and having a normalized trace. So Kahn's embedding conjecture is that every Kahn's embedding conjecture every type 2 sub 1 von Neumann algebra can be embedded in an ultra product of r to the omega. So, well, this omega is for the, actually, over omega of r to the omega, where R is a hyperfinite type 2-1 algebra. So there's a specific type 2-1 algebra, which is essentially the limit of finite dimensional matrices. So you can take finite dimensional matrices and take a limit that makes it a type 2-1 algebra. And so you take this, which is the smallest type 2-1 algebra, and take an ultra product over it, which means you take, so an ultra product comes from set theory, and it's essentially a kind of limit. And so every type 2-1 von Neumann algebra can be embedded, separable. So separable means it's not too big. Every separable can be embedded in an ultra product on r to the omega. So that, so what this says essentially is that any type 2-1 von Neumann algebra behaves something like finite dimensional matrices. And so, you know, the other way, I probably should end soon. The other way, Kahn's embedding conjecture is true if and only if strongly factorizable maps, the set of factorizable maps. To show that Kahn's embedding conjecture implies that, what you do is use the fact that the finite dimensional matrices are dense in R, and then use the definition of ultra product to show that, you know, there's a limit here. So, okay, so if you have any separable type 2-1 algebra, then you can take so it's going to be factorizable. So any factorizable map is going to be factorizable in some von Neumann algebra. You embed it in this ultra product, and then you use the definition of ultra product and the fact that finite dimensional matrices are dense in R to show that there's a limit of finite dimensional, you know, a limit of exactly factorizable maps. Okay, so that is there. So I also want to say that, you know, looking at Kahn's embedding conjecture, if Kahn's embedding conjecture is false, then, okay, so this is something I've just started thinking about. If Kahn's embedding conjecture is false, then there are, I don't know if I have time to say this. So you can look at games you play where there's one player and two other players who are entangled but cannot communicate. This one player can send a state to the first one and the state to the second one, and you can ask what kind of operations can they implement on these quantum states. And if Kahn's embedding conjecture is false, then there are going to be some kind of, I think there are going to be some kind of games which the two players can win if they are entangled via a von Neumann algebra, that they cannot win if they just have, you know, EPR pairs between them. So that is, you know, that, you know, people have been worrying about what kind of games you can win with a quantum system. And if there's a difference between von Neumann algebras and finite dimensional entangled states, I think that's a very interesting result. And I think that is probably equivalent to Kahn's embedding conjecture. And then you can also ask, if you have von Neumann states and you worry about Bell inequalities, can you have can you have states that violate Bell inequalities you can realize with von Neumann algebra that you cannot realize with, you know, finite dimensional entangled systems? And that, I think, is another, you know, really interesting question. And I don't think anybody's thought about these questions, and I think they're, you know, it'd be really nice if you could prove that they're both equivalent to Kahn's embedding conjecture. Okay. So That's really all I have to say, and I seem to have used up my time.
Will you please to say us, in your opinion, to send classical messages with unital matrix is more effectively than any quantum messages?
Any classical messages with unital matrices more effective than any quantum? I think I really don't know how to formulate this question, because with information theory, you know.
We are living in the happy world where is a classical mechanics, classical messages, classical information,
Yeah.
and if we were living only in the quantum world, we have not possibility to most effective sending the information like in classical form.
Right. So, I mean,
your main statement, in my opinion, concludes that there are no quantum Hamiltonian systems, may be time dependent, with help of which, with help the exponent, just effectively approximate unital transformations like in your abstract, most general classic, most general quantum channel.
well, you can embed any classical, I mean, you can consider any classical channel as a quantum channel, so you can embed any you can embed the classical world in the quantum world, so in that sense, the classical world cannot be more efficient. Alexander?
It is a great pity that quantum Birkhoff conjecture is false. For I think this class of mixture of unitary channels is very nice, and as you know, the famous additivity conjecture in quantum probability, in quantum information theory, was shown to be wrong just for this class of channels, of mixtures of unitary channels.
Right.
So if it would be correct, that would mean that for almost all quantum channels you have breaking of additivity, but this is not the case. Was this a kind of motivation for study of asymptotic quantum Birkoff conjecture, or it was different?
I think it was different. So I think, you know, Andreas Winter was trying to. I see that my time is up. Yeah, I have an alarm clock. Which I set to. So, I'm trying to remember what Winter's I think Winter's motivation was more trying to classify channels, but I will have to look at his paper to answer that. Yes?
You wrote recently several papers about quantum money.
Right.
Could you comment please about this?
Yeah, so quantum money is, so quantum money is really an unforgeable quantum state. So what we would like to do is find a quantum state which you can make, but which, if someone else has it, and they also have, and you can also give it to someone and give them a test that will distinguish this quantum state from other quantum states. And what we would like is you can find a state you can make, and you can have a test, And no one who has a copy of the state and has this test can create another state which also passes this test. So really, it's an unforgeable quantum state. So
Maybe I translate unforgeable means неподдельно, то есть те, которые нельзя подделать. Квантовые состояния, которые нельзя, так сказать, фальсифицировать.
yeah. So we have a protocol for unforgeable quantum states, which depends on the difficulty of, so it depends on knot invariance and the difficulty of creating the superposition of all, of all representations of a knot which have a given knot invariant.
Do you mean non-cloning theorem?
Do I mean what?
Non-cloning theorem? Non-cloning?
Is it related to no cloning?
It's related to non-cloning. Well, so it's related to the
You
non-cloning.
want to copy, but you
Yeah,
can't.
right. So you need the non-cloning theorem to show that quantum money is not secure, but it's not sufficient, because if you have a state that you cannot clone and you also have a test to verify the state, maybe you can take this test to verify the state and use it to create a copy of the state. There's nothing in quantum mechanics that says you cannot do this. And in fact, we have a paper showing that in several surprising cases, you really can do this, even though you cannot clone the original state without this verification procedure.
Is verification of this quantum money state is a renewable resource, or it's, you have some certain limit of verification?
So the way in our protocol, the verification degrades the state, but it degrades it only by an exponential amount. So you can repeat this verification exponentially many times before the state goes away.
Practically infinite.
Practically infinite. There is theoretically nothing that prevents it from being theoretically infinite, but we don't have a protocol that satisfies that.
In mathematics, there exist projective limits and inductive limits. We can erase the dimensions and from the finite number of dimensions go to the infinite dimensional limit, or reverse. We can start with infinite dimensional systems, and by rising in codimensional, descend to another limit.
Yeah.
The question is, would the result the same if we use another limit as your present result?
I have not considered this problem, so I don't know the answer.